I am Zeeshan Sattar, and the title of my research paper is Space-Time Turbo Codes Assisted by Fast 4-Symbol Method. This is the outline of my today's presentation. First, I will talk about introduction of the space-time turbo codes. Then I will jump to error flare problem, then forced symbol method, then fast 4-symbol method, followed by the conclusion. So let's first see what is space-time turbo codes. Actually, turbo codes provide us a very good coding gain, where space-time codes provide a diversity gain. So if we want to combine both, we have a combined code, you can say space-time turbo codes. This is the journal block diagram of space-time turbo code which I have used. First we have turbo encoder, followed by modulator, then we have a space-time block encoder. On the decoding side, we have a space-time block decoder, demodulator, turbo decoder, then the small block of fast 4-symbol method. I will talk about it, this fast 4-symbol method in detail in my later slides. For turbo encoder, I have two RSC convolutional encoder connected in parallel fashion. For a space-time block encoder, if we have 2x2 MIMO systems, we can use Alamuti scheme. If we have 3x3, we can use any kind of a space-time block code. So let's a short introduction of turbo codes. In 1993, Barrow and his colleagues introduced new type of codes called turbo codes. They approached within 0.7 dB of the Shannon bound, and earlier this gap was 3 dB. It means before 1993, we have to practically apply twice the theoretical power. Okay, this is the journal block diagram of turbo encoder and decoder. Here, this UK is our information bits, which we encode with two encoders to different encoders separated by an interleaver. Why they are separated by an interleaver? Because at the output of each encoder, we need two different code words. Why we need two different code words? Because at the decoder side, this part of information is decoded by this decoder, and this part of information with this systematic values decoded by this decoder. And now what these two decoders do, they start exchanging their information to improve the soft estimate of the transmitted symbols. So the more they iterate or the more they share, the more accurate soft estimate about a symbol we can make. Okay, so this L of, this L of UK, this is a decision parametric of turbo codes. It's called LLR values as described by Mr. Benjamin. It's composed of three kinds of informations: L priori, L channel, and L extrinsic. This L extrinsic information we calculate from parity bits. This L channel, this information is related to channel SNR as systematic bit, and this L a priori, it is our initial guess about a bit. So when we start guessing, we don't know anything whether it is a symbol, it is bit 1 or 0, so at the very start it becomes 0. So when the decoder 1 and decoder 2 start sharing their information, at first decoder 1 share its extrinsic information with decoder 2, and that information becomes a priori knowledge for decoder 2. Same is the case for in the second iteration, when decoder 2 share its extrinsic information, and the same way they continuously exchange information to improve the soft estimate. Now comes to error flare problem. This is the journal error rate curve of turbo codes or space-time turbo codes, and whenever we use a turbo code with any kind of code, we have this curve. It means first we have low SNR region, then a very good steeper curve of waterfall region, then we have error flare region. People call it error floor, I call it error flare because it's not actually a floor, it's a flare. Okay, so if we need to improve the, you can say, the performance in this region, we can increase the size of the interleaver, or we can just increase fewer more iterations and it can improve the performance in this region. But when it comes to error flare region, we have to increase significantly amount of SNR to improve the performance, or we have to improve the distance properties of the code. So when we talk about the distance properties of the turbo code is related to the design of the interleaver. where we have some mathematical limits on the design of the interleaver that we cannot achieve more than certain minimum distance. And also the design of such complex interleaver is very difficult to design. Now comes to forced symbol method. In 2007, old Sheikh Mohammed and Crozier introduced a method for lowering the error floor for a delay insensitive power saving applications, such as the case in deep space and satellite communication. The point to be noted is delay insensitive, because whatever this method is all about, it caused a huge delay. FSM can roughly approach the square of the original error floor performance. It means if for a certain code I can approach to a frame error rate of 10 raised to the power minus 3 or minus 4, by using this method, you can approach to from minus 4 to minus 8. And for this method, we don't have to use any parity bits, and we don't have to do any kind of big change in the design of the decoder. Okay, so how this FSM works? This FSM applies repeated decoding operations with one or more symbol being forced to certain values when an error is detected using an error detection method. It sorts the magnitudes of priori LLRs of all information bits in ascending order. I will explain the slide with a graphical representation. First, this is a journal, you can say the graph of LLR values. Now, if for a certain bit this LLR value comes here or somewhere here, I can say the decision which I'm taking about a certain bit is very good. If it comes here like minus 4, minus 3 or more minus 10, we can say it's a very good reliable decision. But when this decision comes in this region, I mean close to this axis, we can say the decision which I'm taking about a symbol, that it is 0 or 1, it is not very reliable. So what we do in forced symbol method, we sort the magnitudes of LLRs in ascending order. Like here, let's suppose the most smallest LLR which we have calculated for a transmitted signal is minus 0.2. Then what we do, we are assuming that this symbol is, we have decoded it wrongly. So we force it to change our decision. Then we decode again and again check with CRC. If it works fine, we leave it. Otherwise, we again decode and flip the second symbol. And we decode continuously until and unless we check all the symbols. But the interesting thing is that we should come in mind that why forcing one symbol can correct more than one errors. Because what I'm saying is, if I just force one symbol, it can correct more than one errors. Because when it comes to trellis diagram, which we use in convolution encoding, turbo encoding, each decision, you can say, gives a positive effect on other decision. So a strong decision, as I'm saying, I will force my second symbol, it will push other symbols to have a correct value. Okay, I'll just briefly describe this. This LLR of turbo codes, this L values, it is composed of three, you can say three matrix. The first is alpha, this is called forward metric. This beta is called backward metric, and this is called transition metric. So as I was saying that if I force one symbol, it can correct more than one errors. You can see from here that each value of alpha, it depends on its previous value, where each value of beta, it depends on its future value. So from here we can see that just forcing one symbol can correct more than one errors because it has an effect on whole trellis. Okay, now comes to fast force symbol method. The core of the FFSM is its ability to find a set of positions which have more potential to be in error when decoding of a given frame fails. Like in force symbol method, what we were doing, we were just forcing the most unreliable symbols, where in fast force symbol method, we are trying to find the positions of those symbols which we think that have more potential to be in error. This new method exploits the concept of scaling of extrinsic information. The effect of a scaling factor is to combat correlation effects in the iterative procedure. Since practical turbo codes rely on finite blocks, extrinsic and intrinsic pieces of information become more and more correlated with successive iterations. This is the flow chart of my work. So when we received our symbol at the receiver, first we give to space-time block code, which give the soft estimate to turbo decoder, where turbo decoder do standard turbo decoding. If it fails, it again decode with a scaling factor of 0.8. Scaling factor means the information which I'm sharing with two decoders, I will just multiply with 0.8, then I will decode again. If again decoding fails, I will decode again with 0.7. The thing is, sometimes even just by scaling, using the scaling factor corrects the errors. And the more interesting thing is that after decoding with these three, I mean, we have now three decoded sequence, first with scaling factor of 1, that is standard, then with 0.8, then here we have with 0.7. Now we have three decoded sequences, and if we observe the unreliable symbols or positions of unreliable symbols in these three decoded sequences, they are different. For example, in this case, if symbol 1 is most unreliable, so maybe for this case, symbol 4 is the most unreliable symbol. And at the end, what we need in 4 symbol method is a group of symbols which don't have a good reliability. So now what we do, we take bunch of few symbols, unreliable symbols from here, and from here, and from here. Then we sum up, take a union to cancel out the repeated values, and then we force these symbol positions one by one to take the opposite value of the original estimate. Okay, these are my simulation results. The first result is for standard turbo decoding, where I am comparing my result, this max log map, this is the standard turbo decoding, and here are my results FFSM, and you can see we have achieved around 0.75 dB of gain. The second result is for space-time turbo code for 2x2 MIMO systems, and I have one more results. This is for 3x3 MIMO systems. Okay, why my scheme is faster than its predecessor? Because FSM at 0.5 dB it do 583 times repeated decoding, at 0.75 it's do 273 times repeated decoding, where if you just compare my results, it's like 40, 26, 15. So it means by using this FFSM, we can hugely reduce the computational complexity. Now comes to the conclusion. The proposed FFSM reduces significantly both the peak and the average decoding complexity of the standard FSM, while achieving essentially the same error rate performance as of the FSM. The simulation results show that a gain of 0.75 dB at frame error rate of 10 raised to the power minus 5 is achieved with the FFSM when compared to standard space-time turbo codes. Thank you very much.